Let's look at a slightly interesting geometric problem. What's the volume of a torus? A torus is the math word for a donut-shaped thing. A torus is the Greek word for bull or an old model of a car. So here I have a torus. So how could you mathematically describe this? You would agree it's donut-shaped, right? But if you were to draw maybe a cross-section on your two-dimensional paper, what would be a good way of drawing that? So take a sec to do that. So one way you could see it is I have a cross section over here that's a circle, and another cross section over here that's a circle. So I've taken this and kind of chopped it here, chopped it there, and then laid it like that. So what is there to say about a torus? What will help me figure out the volume of this torus compared to an actual donut, for example? Something about radius, and is there just one radius? Well, some people, especially people in the construction trades, might talk about, well, there's the inner radius or inner diameter in some case, but here we'll use radius. That's to this point here, and they might also talk about the outer radius, and that's a good way of thinking things. But it turns out to be slightly more convenient mathematically to think of it a different way. Can you think of a different way of talking about what's going on with this circular thing? Well, you could say what's happening is I'm taking a circle of this cross-section and rotating it all the way around. So you could say I have a radius to the center here, and I'll call that capital R, and then I have something that tells me how big this cross-section is. Is it like that? Is it like that? So I could say from there on to the edge is maybe little r. So that might be a good way to parameterize it. And then how do we want to draw a differential element? Here we are in chapter 7.2. How am I going to slice this thing up and think about adding up volumes of slices? Do you think disks, washers? We should say the rotation we're imagining here is around the y-axis. So we're kind of looking at it like this. So what do you think? Disks, washers, which orientation? I think natural for this one would be to kind of slice it like that, almost like you were gonna, like the first cut could be just slicing it in half, like you would slice a donut or a bagel. And then we'd have another one over here, and then we'd have the disc, the washer connecting that. So that's a nice way of thinking of it. So then the next question to set up our integral is at, so this is the inner radius of the torus and the outer radius of the torus. But then now we're going to start thinking about the inner radius of the washer and the outer radius of the washer, right? That's what our formula has. So we're going to have all these slices at different y values, and we need to answer the question, at any particular y value, what is the inner radius and outer radius of the washer? We know what it would be at the center, right? It would be the big radius, the big R minus the small r would be the inner radius, big R plus little r would be the outer radius. We could figure it out what it would be up here. What would it be somewhere in the middle? That turns out to need a right triangle, maybe. So that's something to think about. And then we'll come back to this problem later in chapter 7.3 and imagine slicing it up another way.